Let's look at some of the preliminaries of the algebra. It is an algebra of operators that operate on relation instances, which is to say tables full of tuples, so specific tables. And you can cascade these operators in nested expressions like the ones here. And you'll see at the innermost level of these expressions, we've got letters like R and S that represent these relation instances. Important to note that the operators of the algebra are closed, so the result of any relational algebra expression is a relation instance. This means we can compose together long strings of relational algebra operators and keep adding to them as we go, because everything is mapping from relations to relations. Another thing to note is that everything is typed in this language. Obviously, the relation instances have schemas with column types, and the operators have definitions for the schemas of the output based on the schemas of the inputs. And as a result, you can statically check whether queries are legal or not. And so this is all a neatly typed system. Now, the relational algebra in its purest form has a set semantics, so there's no duplicate tuples in a relation instance in the relational algebra. Recall that this is different from SQL, which has a multiset or bag semantics, where it keeps track of all the duplicates very carefully in each table. So we're going to switch to multiset when we start talking about systems and SQL again. But for the next few slides, as we're just learning the basics of the relational algebra, we'll focus on its pure form, which is in terms of sets with no duplicates. There's really very few operators in the algebra, so let's go through them. First, we'll start with the unary operators, which is to say operators on a single relation instance. So the first one we'll look at is projection. Projection retains only the desired columns from a relation, so it sort of vertically chooses columns that we're interested in. Selection, on the other hand, selects a subset of the rows that we want from the table, so it's a sort of horizontal choice of entries in the table. Renaming is an operator really for just sort of syntactic convenience to allow us to make sure that we can assign names to attributes and to relations after they've been manipulated by other operators. And here are the remaining three operators in the relational algebra. These are binary operators that operate on a pair of relations like R1 and R2. So union takes all the tuples in R1 or in R2, which is to say the union of all the tuples, obviously removing duplicates because we have no duplicates in the relational algebra. Set difference takes those tuples in R1 that are not in R2, and then cross product allows us to combine two relations in a way that you're probably familiar with. Now, there are only 6 operators in the algebra so far. We're going to go through each one of them in detail. But before we do that, there's a couple convenience macros or compound operators that put together some of the above operators, but they're so frequently put together that we assign sort of names to them. One of them is intersection, which finds the tuples in R1 that are also in R2. And the other is join in its various forms, which is the way we combine relations to satisfy predicates. Let's go through each of the operators in detail, and we'll also go through these compound operators or macros. We start with projection. So here's an example of a relation instance S2. It's our old Sailors table. And we're going to write projection with the letter pi and a subscript for the list of attributes that we want in the output. So the projection of S2 onto SName and age is what you see here. It's the SName and age columns from the original table, producing a new table with just 2 columns. This corresponds to the select list in SQL, right? The list of columns that we wanted in the output of our select query. It's very annoying that the word select is used in SQL to mean projection in the relational algebra, but it is the way it is, so try to remember that. The schema of a projection is determined by the schema of the attributes in the attribute list. So we know that SName is text and age is integer. We know that from the input S2, and it defines the schema of the output as having text and integer as the two types of the 2 columns. In the end, what projection is doing is selecting a subset of the columns from the table. Let's look at another example. In this example, we're going to take the projection of S2 onto just the age column. Now, you might think that we just copy over the age column, but you'll see that that's actually a multiset. It's got duplicates. The actual output of this in terms of relational algebra is a set with 2 values, 35.0 and 55.5. So you can see that duplicate elimination is part of the definition of projection because we're in a set semantics in the relational algebra. Now, in real systems, we might not automatically remove those duplicates. You might ask, why not remove them? Well, 2 reasons, semantics and performance. So on the semantics side, In real systems, sometimes it's useful to know the number of duplicates, for instance, for aggregation queries. If we want to average up, say, the ages of all the sailors, we would want to keep all those instances of 35.0. Moreover, in some cases, we just don't care if there's duplicates in the output. We're perfectly happy to see those duplicates. And in that case, we might not want to pay to remove them. And by pay, I mean run an algorithm like sorting or hashing to do duplicate elimination. So we can avoid doing sorting or hashing if we simply tolerate duplicates in the output. So those are two reasons why real systems, SQL systems in particular, don't automatically remove duplicates, but often will allow you to remove duplicates if you want to. And as we saw, projection is selecting a subset of columns. Now let's look at selection. Here's an example. We've got a selection, which is represented as the letter sigma, lowercase sigma, with a subscript that is a Boolean predicate. It's a condition over columns of the input. And then, of course, this operation is placed over some relation instance. So this is read as select from S2 where rating is greater than 8. And if you look at the table S2, this is going to rule out that tuple, and it's going to rule out that tuple, and it's going to leave us with an answer set that looks like this. This corresponds to the where clause in SQL, not the select clause, which is projection, but the where clause. I know that's confusing. So it is. The output schema of a selection is the same as the input. We have the same number of columns in the same order with the same types. And duplicate elimination is not needed in selection. Remember, the input to the selection is a set. We're only removing things from it, so we couldn't have generated any duplicates. So the output is by definition also a set without duplicates. And selection in the end is selecting a subset of the rows. It's a sort of horizontal selection of things we want in our output. Now that we have two operators, we can write a larger expression that composes them together. So here's an example. We're going to find the names of sailors with rating greater than 8. So we can write that as a selection, sigma, with rating greater than 8 of our table S2, followed by a projection on S name. And so we can think about this operationally as taking that table over on the left, applying the selection, sigma rating greater than 8, to get just those two tuples, and then applying the projection to those two tuples to just get the S name column, which has Yuppie and Rusty in it. Now, let's look at one more example. What about this one? Select rating greater than 8 over project to S name of S2. This one, it turns out, doesn't type properly. So think about it. The projection of S2 onto S name only has one column in its output, S name. And so when you try to apply the selection of rating greater than 8 to it, there's no rating column left to apply that selection to. And so the input to the selection does not contain the columns referenced in its subscript, which is a type error. Okay? So you can't always commute these operations, as you can see.